Hi there. Welcome to another edition of the Yugabyte DB Tech Talk series. My name is Sid Choudhury, and today I'm going to walk you through Spanner versus Calvin, comparing consensus protocols in strongly consistent database systems. Let's dive right in. First of all, why strong consistency? The answer is actually very simple. Strong consistency helps developer agility. It ensures that developers of distributed applications can write to the database and then read from the database the same data that they had written before without actually going through a complex matrix of corner conditions and ensure that the end user actually continues to see correct data. On the operational front, there is operational simplicity by using a strongly consistent database by ensuring that things such as node additions, node removal, ensuring highly dense data sets can be stored inside the database. All these are very important aspects as we move towards cloud native infrastructure and cloud native databases. The second question is why global consistency? And for that, I want to walk you through an example. Imagine this is the database cluster powering Google.com. And there we are accessing, users are accessing that data from across the globe. Now, if different users get different results for the same queries, then probably for search it may be okay. But if we're talking about their Google Ads inventory, then it may not be okay. Because a user may mistakenly believe that their organization has more credits in Google Ad than it actually has, and schedule their ad to be served by Google, but Google will not be able to do so at the last minute because their ad inventory was or their ad credits were not there. So at the end of the day, global consistency is a big driver towards ensuring happy customers. Let's look at the two big database architectures that are coming up for building strongly consistent, globally distributed systems. First is Google Spanner. Google Spanner was actually introduced to the world in a conference in 2012, and this is one of the slides from that conference. Google had been working on such a global database for a few years by then, and this is the first public forum where they introduced it. Even in a distributed architecture, there is support for ACID transactions, something that was unheard of around that time. And it supports the full spectrum of SQL, the structured query language, which is essentially the lingua franca for operational database systems. And that is the system that actually powers Google's ad infrastructure, including the Google Ads credit problem that I highlighted before. And it actually replaced a sharded MySQL database infrastructure at Google, and the results were phenomenal at that time. Architecturally, Spanner is a very interesting system in the sense that there are data centers, and each data center can have multiple zones, and each zone can have multiple has a zone master, and that zone master through the location proxy knows where actually data is located and in the multiple span servers that are allocated in that particular zone. So so that as new data comes in, the data just keeps getting distributed across these zones and gets persisted in these ever-growing number of probably hundreds and thousands of span servers that are present. One of the big additions of Spanner to the database research is the notion of globally distributed ACID transactions. And the way Spanner does that is through two components. One is through the use of Paxos for single shard transactions and replication, as well as a two-phase commit for the globally distributed transaction problem. Plus, and very importantly, there is a hardware component that kicks in the notion of distributed transaction, and that is called true time. True time is essentially gives the notion of a single wall clock to all the various nodes or span servers in the system, so that as nodes are participating in transactions, they know exactly how to order the various transactions in a system, and as a result, dirty data never gets served or gets persisted into the database. Now, this was an architectural marvel in 2012 when it was introduced. Around the same time, a different global consistency paradigm was introduced, and it was called Calvin, out of a research team at Yale. Calvin was called as a practical transaction scheduling and data replication layer that uses deterministic ordering guarantees. And we'll look at what does deterministic ordering guarantee actually means, to significantly reduce the prohibitive contention cost associated with distributed transactions. So when transactions are trying to update the same data, Calvin ensures that it can deterministically order the sequence of those updates. As a result, there is less contention, and there is a clean linear ordering of the various operations. Architecturally, Spanner has the notion of these sequencers, which is where the data which is where the clients are actually interacting. And however, there is only one sequencer in this entire cluster, which is actually the leader, and it's called the global consensus leader, that takes in the writes in the system, ensures that it is able to do the deterministic ordering, and then sends it down to the schedulers to actually schedule those changes onto the actual storage nodes. So in terms of architecture, it's a much simpler architecture because there is a single global consensus leader that is ensuring the ordering guarantees of both single shard as well as distributed transactions. Note, there is no dependency on clock skew as such, because two nodes are not competing to write the data with their own notion of clock in this system. So these are some of the key differences between Calvin approach and Spanner approach. For single shard transactions, Spanner uses per shard consensus. Each shard inside Spanner has its own Paxos group, and whereas in case of Calvin, there is a single global consensus, which can be Paxos or Raft or some other distributed consensus protocol. When it comes to multi-shard or distributed transactions, Spanner has to use a two-phase commit to make sure every shard who owns a piece of data in that transaction participate in a global ordering scheme. Whereas Calvin uses deterministic serial ordering on the global consensus leader that we just talked about. The net result at the end of the day is that from a language standpoint, Spanner has ability to support the full spectrum of SQL, including secondary indexes as well as session transactions, whereas Calvin loses support for things like dependent transactions, which are foundation for session transactions, and as a result cannot support the complexity of SQL as a language. Now, that both the protocols were introduced in 2012. Since then, new databases have come to the market who have taken inspiration from each of these architectures, and those are the ones we're calling as the derivatives. Let's look at the battle of the derivatives as to how that stands. So Spanner has actually two derivatives. One is Yugabyte DB, and we at Yugabyte DB are excited to have taken inspiration from Spanner for a bunch of reasons that we'll talk about. Another database that is also inspired by Spanner is CockroachDB. On the Calvin front, there is so Calvin did not have any, since it was invented in academia, there is no real-world practical implementation available on day one, whereas Spanner was Google's primary revenue intensive database engine. And so in case of Calvin, there is only Fauna DB, which is another database product that built its architecture on top of Calvin. So let's look at a bunch of axes around how Calvin and Spanner and Calvin actually impact the design of these individual derivatives. First is correctness. So, and that actually manifests itself in terms of the isolation level in your ACID transactions. And in case of Spanner, since there is a dependency to track clock skew and essentially stop the nodes from participating in distributed transactions if the max clock skew is exceeded, the maximum isolation level that is possible is serializability. And that works great for most practical cases where clock skew remains bounded. The notion of clock skew jumping from those bounds of 100 milliseconds or 200 milliseconds is very rare in today's, especially in modern public cloud systems, as we'll look later in the talk. Calvin, on the other hand, has no dependency on the clock skew, and as a result is able to support strict serializability through its global consensus approach. Now, if your environment is very much dependent on clock skews and the need to track it from a very close quarters, and then you may require the theoretical correctness guarantees that Calvin espouses, whereas Spanner is a very practical system. Transaction model, touched on that a little bit before. Spanner's transaction model is very rich, can do dependent transactions involving secondary indexes where there are two keys actually involved in a single update. Session transactions is when you don't know the full scope of your transaction and the client is actually interactively working with you over a shell or using an ORM. And that makes it as an excellent engine for a SQL compatible database. Whereas Calvin has a very weak transaction model with poor support for secondary indexes because there will be a lot of restarts in a Calvin-like architecture for transactions that have this notion of secondary indexes. And there is absolutely no support possible for session transactions because Calvin requires all the transactions inputs to be pre-processed in the sequencing layer before it submits to the storage engine. So there is no possibility of you submitting the transaction, various operations in the transaction one by one. This makes Calvin fit for only a non-SQL API layer, which is a NoSQL database. Read performance. Now, Spanner can actually serve reads really fast from for the various keys from their individual shard leaders. Those shard leaders do not have to talk to any other replica in the system, and each shard leader can use the resources of the node it runs on. The net results is that low latency reads can be served, and that too lots of reads can be served in the system, and that leads us to high throughput. Whereas in Calvin, the global consensus leader, current leader, is actually a single point of bottleneck in the system. If it is getting overwhelmed, then you will see high latency because it has to actually process each and every transaction or each and every read that is coming in. And it does also have to talk to, and it actually cannot do more of those operations. So read-wise, Spanner is a clear winner. Write is where it gets a little bit more interesting. In case of Spanner, Spanner has low latency for single shard transactions because the single Paxos group responsible for that particular shard and its leader is able to take care of that transaction, which means that in order for Spanner to shine, you need to be talking to lots of random shards at the same time. So that there are concurrent access into the cluster, but each access is hitting some different piece of data point. So high throughput for concurrent access to random data is Spanner's forte. Calvin has a different approach. It has low latency it has higher latency for single shard transactions because the focus is on primarily distributed transaction heavy workload and doing the sequencing guarantee on top of all the keys that are present in the transaction. As a result, it gives high throughput only if there is concurrent access, but to the same set of keys again and again and again. Very different in the two workload types that they support. Fault tolerance. I think you can easily see where Spanner sort of goes leaps and bounds ahead of Calvin here because of its fully decentralized architecture with no single point of failure. Node failures, whenever they happen, they impact only a subset of shards. As a result, write enableability is actually limited to those shards only. And net result is that the fault tolerance level of the system is extremely high. Whereas on the Calvin side, the global consensus leader is a single point of failure. It's a performance bottleneck and it is a single point of failure. So when that node specifically dies, there is write unavailability for all data. Now, because of use of Paxos, a different leader will be chosen, a different global consensus leader will be chosen, but that doesn't take away the fact that your writes are essentially unavailable across the cluster for the full set of data. Clock skew mitigation. It's a very important problem. The way Spanner derivatives optimize for clock skew is they try to integrate with true time-like APIs available from Amazon, Google, Azure. Each of the public clouds are very much invested in making those APIs available to workloads running on them so that more distributed applications can be brought onto those public clouds. So as a result, Spanner architecture is more optimized for the public clouds where the clock skew can be bounded even better than the traditional NTP approach using the APIs of the cloud platforms themselves. Calvin, on the other hand, has no dependency on clock skew, and typically in on-premises environments where clock skew jumps can be extreme because those are managed. Each of those nodes are managed out of band, probably using different processes than what the public clouds use. Then Calvin can be a better approach. So Calvin is on-premises data center optimized as opposed to Spanner, which is public cloud optimized. Coming to open source, both the Spanner derivatives, Yugabyte DB and Cockroach DB are Apache 2.0 projects, highly permissible license. You can read the code, modify the code, fork the code any which way you like. Whereas on the Calvin front, FaunaDB is a fully proprietary software. So you have the risk of recreating the challenges of proprietary software database era of the big three, Oracle, SQL Server, and IBM DB2. Finally, let's talk about APIs, because as developers, we interact with those APIs day in and day out. Spanner derivatives, Yugabyte DB supports wire compatibility with actually 3 popular open source databases, Cassandra, Redis, and PostgreSQL. Whereas Cockroach DB, the other derivative, is only PostgreSQL compatible. Calvin, on the other hand, which is FaunaDB, uses a proprietary and custom query language with no existing, no pre-existing ecosystem to actually, give the developer the productivity that is needed on day one, and actually leads to, significant vendor lock-in on day 2 as you want to, expand your database investment. So with that, I bring you to the summary. Spanner beats Calvin for most common OLTP workloads because traditionally those kinds of workloads use have high concurrent access to random data, and when the data is sort of randomly evenly spread across the cluster, you get all the benefits of read performance, write performance, and high fault tolerance while remaining SQL compliant. And both the Spanner derivatives are fully open source. So that's another, I would say, the icing on the cake. Calvin has a very narrow or niche workload optimization around concurrent access to same data and again, with no support for SQL and all the proprietariness that comes from FaunaDB. We have explained all of this in a blog form. Here is our blog post. Recommend you take a look at that. And Yugabyte DB, as I noted, is fully open source. You can take a look at our GitHub project and actually try on your laptop as a local cluster. You can do a very easy quick start where you can see all the multiple APIs in action, explore each of the APIs in fair amount of detail, and let us know what you think. With that, thank you for tuning in today, and hope to see you next time at a future edition of our Tech Talk. Bye.